then I know that x dot is equal to what? Omega A. So x dot is equal to omega, which you've just found is 5 root 30 over 3, multiplied by A, which is 0.15. And that gives us... Anyone got it?
Root 30 over 4.
Is it root 30 over 4? Can someone concur? 1.37. 1.37 metres per second. Okay, so that's the answer for that one there. Right, part E. Part E, back there, that's what it says. Find the speed of P at the instant when the spring has returned to its natural length. Okay, so find the speed of P the instant when it has returned to its natural length. So here we go, back over the page. Right, so what goes on is that, going back to its natural length, do you agree that its natural length is when you've got a situation, there's no need to draw a sketch here, I'm just doing it to make it obvious to you. There's its natural length here, 0.6 I think it was, wasn't it? Mm-hmm. Okay, that was E, which was 0.1176. Okay, that was the centre of oscillations there, and we were originally, would have gone down to 0.15. Okay, so we've got all those dimensions on here. What's happened is it was dropped from up here, or crushed in because it's a spring, shot down to there and come back up. So the first the speed here is what we want. Do you agree? Right. So the speed there, what would you do? What does x equal? Well, it doesn't matter. Why does it matter? Doesn't it matter? Let's look at what the speed equation is. Squaring it. X dot squared is equal to omega squared brackets a squared minus x squared. Now, because we're squaring it, you are right. It doesn't matter. But yeah, usually just be careful about what's going on here. So x is equal to in meters, 0.1176. So x dot squared equals, what was the omega again? It was 5 root 30 over 3 all squared, all multiplied by a, which is 0.15 squared, take away 0.1176 squared. Okay?
0.724.
Anyone verify that just to make sure? 0.723 metres per second. Did you square root it?
Square root is 0.85.
Oh, right, so square root that, so that's not metres per second. So you get, what do we get?
0.850.
0.850, and that's metres per second. And you get a plus and minus. Why do you get a plus and minus there?
It'll be going to
That's it. It'll go the same as it goes out. When it hits there again, it'll come back down. It'll be the same speed, equal opposite. No, because you're under the tension takes all that up. Okay, right. Is everyone happy with that?
Yeah.
Is that the last part of that question?
Yeah.
Yeah. Okay. Right. Over the page. Example 15. Now, a particle of mass 0.2 kilograms is attached at one end of a light elastic string of natural length 0.6 and modulus 8 newtons. The other end of the string is fixed to a point A on the ceiling. When the particle is hanging in equilibrium, the length of the string is L. Calculate the value of L. So my diagram for part A would simply look like this. It'd go like that. It'd go bang, 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 bang is the ceiling. It's an equilibrium. So I've got that is 0.6 metres, okay, and I've got that there is the extension E, and then I've got my particle here, which I think was 0.2. So that's 0.2. That going down there is 0.2 G. That going there is T, and the dimension I want is, as it said, that there is L, I think it called it there. So the length of the string is L. When the particle is hanging in equilibrium, the length of the string is L. So that's the length of the string L. So we've got Hooke's law. Hooke's law says that the tension is equal to lambda, which is 8, and I suppose I can fit that across there. Lambda is 8. Box it off. Is 8 times the extension. Now, I don't have to use E. I might as well just use, in terms of L, it is going to be L minus 0.6. Okay, so times extension all over the natural length, which is 0.6. Then Newton's second law, I'm going to say positive is, positive is upwards for a change. Okay, and that starts me off with T minus 0.2 G. It's in equilibrium, is equal to 0. So my T, which is going to be 8 over 0.6, multiplied by my L minus 0.6, minus 0.2 G is equal to 0. Okay, so we've got to expand this out. So we've got to do 8 divided by 0.6, 8, 40 over 3. So I've got 40 over 3 L and 40 divided by 3 multiplied by 0.6 and gives you 8. So minus 8 minus and a fifth of that, so 0.2 times 9.8, and you should have got an answer of 49 over 25. Oh, this did actually be a nice number, 1.96. 1.96 is equal to 0. Therefore, L is equal to, add those two together and throw it over, makes 9.96 multiplied by 3 and times, divided by 40. And has anyone got that answer? 0.747 metres. Right, so that's the answer they want, but later on I probably will want, and I'll put it in brackets, the extension is equal to, and take 0.6 from there, it is going to be 0.147 metres, just in case I need it for later on. Okay. Right, so I've got to calculate the particle is held at A and released from rest, so it's a string, so it's all slack. It first comes to instantaneous rest when the length of the string is k metres. Use the energy considerations to calculate the value of k. So what we've got here, we've got another diagram B. Okay, there's the said ceiling. And how I usually signify this is I've got my particle there, and then I end up showing you what it's going to look like, which is down here. We've got at this stage here, I've got my L. Then at this stage here, so that's the centre of oscillation. At this stage here is my lowest point. Okay, the mass is 0.2, and that distance now down there is k. And my natural length I will put on is 0.6, and my E there is 0.147. In just case I need it, I don't know where I'm going to go with this. Well, I'll do, but here we go. Energy considerations. How I set this out is I do mechanical energy before and mechanical energy after. Now I look at it, and it was released from rest, and it's first instantaneously at rest. So kinetic energy is, and kinetic energy afterwards. So potential energy. Now I will put on here the lowest point at this stage here, a dotted line, and I always call it, and you should call it P capital E with subscript 0. Okay, so my potential energy, of which I have got some, is equal to mgh, so it's 0.2 m g, so times by 9.8 times by h, the height, which is going to be k. Okay, so I'm going to just quickly work that, a fifth of thingamajig. What's that again? We've done that before. So 0.2 times by 9.8 equals 49 over that, and 1.96, isn't it? Yeah, we did that before. So we've got is equal to 1.96 k, and it's that many joules in brackets. Okay, right. There's no elastic potential energy because it's at it's slack. I've got no kinetic energy, as we mentioned. I've got no potential energy because we're down here, and the only thing I've got is elastic potential energy. EPE is equal to, now if you remember the formula, it is lambda, which was 8 times the extension squared. Now the extension is going to be all the way down here is where we're at, and therefore the extension is simply k minus no 0.6, because that's still extended. This bit is still extended, yeah. So it is extension is k minus 0.6, and don't forget it's the extension squared all over twice the length, which is 1.2. Okay, I'm going to set these two equal. If I can just work out what 8 divided by 1.2 is. 8 divided by 1.2, 20 over 3. Okay, minimise that. So I've got 1.96k is equal to, was it 20 over 3 I just said?
Yeah.
20 over 3 lots of k minus 0.6 squared. And I'd usually put MEB is equal to MEA above that. Okay. Times through by 3 and divide by 20, so that allows me just to expand that then. So 1.96 times by 3, divide the answer by 20, and we get an answer of SD at 0.294. 0.294k is equal to, expand this now, is just k squared. That times that doubled is minus 1.2k, and that squared is positive 0.36. Get everything onto the right hand side, form a quadratic. K squared, bring that over to give you minus 1.494, is it? K, and I've got plus 0.36. Now I'm not going to mess around, I'm going to go straight to the quadratic formula. The solutions are k equals minus b, so that's 1.494 square root of 1.494 squared minus 4ac, so minus 4 lots of 0.36, because a is 1, all over twice of a is 2. Oh yeah, I missed that plus and minus. Okay, a rather critical bit. So I'm going to do the plus first of all. So fraction button, I've got 1.494 plus the square root of 1.494 squared minus the answer to 4 lots of 0.36, close brackets, scroll out and scroll down, and end up with 2 equals 1.1936 fig. So I've used G. So what have we got? K equals 1.19 meters, and you can see we've got problems if we go back and did the negative. Okay, delete and put a minus, press equals. Why can't that be the case? Okay, the natural length is 0.6, and you're less than that, so it's not possible. Okay, so that's the answer. Okay, was that what we wanted? Was the value of k? Yeah, it was just k it wanted, wasn't it? Right. It says show that while the string is taut, P is moving with simple harmonic motion. Say again. Why did I not leave space over the page? Ah, well. Just put it on a piece of paper and just glue it to the bottom or something. Okay, so that means that means I can't as well. I've run out of space. There's no paper over the thingy. So I'm going to come back up here. I'm going to have to do it here. Okay, so with. Okay. Right, so simple harmonic motion. I'll draw a sketch. This is for part C. The sketch looks like this. Now, how did I suggest that you always do this? Pick a general point that is below the equilibrium is how I'd do it. Okay, so only a general point. I would label that as 0.6. I would label that myself as 0. I mean, there's all other ways you can do this. 0.1176 is the extension. I would put a dotted line there because that is the equilibrium position, the centre of oscillation position. And then I would show a general point down here with my particle on it, and that general point would be labelled as X. And if that's the case, then the arrow needs to be going in the direction of X increasing, which will be that way. So X dot dot is that. So I will need to put on there, which is, was this 0.2? 0.2.